Two events are independent when the outcome of one doesn't affect the probability of the outcome of the other. When we have independent events A and B, the probability that they both occur together, the probability of A and B, equals the probability of A times the probability of B. Let's say you flip a coin twice. Let A be the event that you get heads on the first flip. Let B be the event that you get heads on the second flip. Are A and B independent? Yes, because if A occurs, it doesn't have any effect on the occurrence of B. The probability of heads on the second flip is 1/2, regardless of what happens on the first flip. If you flip a coin twice, there are 4 possible outcomes. You can get heads, 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 tails, tails, heads, and tails, tails. And all of these are equally likely, so they all have probability 1/4. The probability of getting heads twice is 1/4, and 1/4 equals 1/2 times 1/2, which is the probability of getting heads on the first flip times the probability of getting heads on the second flip. You can see that this satisfies our definition of independence. Now, I'm going to have A and B count the number of heads. Let A be the number of heads on the first flip, let B be the number of heads on the second flip. So A can equal 0 or 1, and B can equal 0 or 1. If we look at it this way, we get the same result. The probability of 2 heads is the probability that A equals 1 and B equals 1. And that's 1/2 times 1/2 equals 1/4, just as we got before. I want to change the experiment a little bit. Now, if you get heads on the first flip, you flip 2 coins for the second flip. If you get tails on the first flip, you still only flip 1 coin for the second. Now, A can equal 0 or 1, but B, which counts the number of heads on the second round, can equal 0, 1, or 2. Now, the outcome of A affects the probabilities of the outcomes of B. If you get tails on the first flip, A equals 0, and the probabilities for B are like this. But if you get heads on the first flip, the probabilities for B are in this other column. Thus, A and B are not independent. Say we have 2 events, A and B, that are independent. Then we have P, A, and B equals P, A times P, B. If we bring in another variable C that's independent of both A and B, then it's also independent of the event A and B, which is this thing there. And so we have P, A, and B, and C equals PA times PB times PC. And we can keep adding as many variables as we want as long as they're independent. In other words, you can chain this result. And this is actually a pretty important result that will be underlying a lot of what we do in the course. Let's look at an example from the book. This is problem 310 on page 93. In a multiple choice exam, there are 5 questions and 4 choices for each question, A, B, C, D. Nancy has not studied for the exam at all and decides to randomly guess the answers. What is the probability that the first question she gets right is the 5th question? What we have here is that the probability of a right answer, PR, equals 1/4. And the probability of a wrong answer, PW, equals 3/4. They're complementary events because she can't be both right and wrong. Because there are 4 options and she's just guessing, notice that her answer for each question is independent of all the others, because randomly guessing one correctly wouldn't affect whether she's correct on any of the others. What is the probability that the first question she gets right is the 5th question? That would be the probability of the sequence WWWWR. 4 wrongs and then a right. We can use the multiplication rule and find that the probability of this sequence is 0.079. Part B asks for the probability that she guesses all the questions correctly. That would be the sequence R, 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 R. The probability of this is 1/4 to the 5th power, which is 0.00098. Finally, we want the probability that she gets at least one question right. If you think about all the sequences of answers that have at least one R, there are a lot of them. She could have R, W, 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 R, R, W, R, W, W, R, W, R, and so on and so on. Anything that has at least one R is a possibility. Instead of trying to deal with all of them, it's easier if you notice that the event that she gets at least one question right is the complement of the event that she gets no questions right. We can find the probability of getting no questions right, PWWWWW, and subtract it from 1. And that is 0.7627. So she's got a pretty good chance of getting at least one right. Make sure you only use this multiplication rule if A and B are independent. If A and B are dependent, then the probability of A and B will depend on their specific relationship. There's no one formula for it.